Cool. So we're going to have a quick chat just for 20 minutes about performance analysis. This is a very important part of the course. It's probably one of the most important lectures in the course in a way. It's not necessarily like the lecture that has all the necessary information to like do everything, but like the concepts we touch on in this lecture are probably like the most paramount part of the course. Like when I think about 2521, I think about a lecture like this, and we'll do more of this stuff in the course. This isn't like all or nothing, but let's get stuck into it. And thankfully a lot of it starts with the timing, which we've already done. So what is this lecture and why does it matter? Well, understanding how different data structures and algorithms, data structures in arrays, linked lists, and algorithms like, Fibonacci, factorial, stuff like that, how these programs interact with time and memory, processing and storage, whatever, is really critical to help you write the right programs. Thankfully, we've already touched on this, right? We had a look at those two recursive factorial functions, and we said, which one is better? Well, one of them uses more memory. One of them takes longer, maybe. Some of them are like simpler to write. There are differences in how these things are, and it's important that we have the capacity to analyze these things. So what we'll be covering in this lecture today and then next week as well is we'll be talking about data structures, like arrays and linked lists. We'll be talking about algorithms, which is a big part of it. We'll be talking about pseudocode, which is a way to kind of write draft code, if you will, like before you actually write it. And then we'll be talking about how to analyze how long a program takes to run, and then a little bit of how much memory it uses. But we're kind of just touching on that really lightly because we're not deep enough into the course to meaningfully kind of cover that yet. So first thing, measuring the literal program runtime. So we started doing this in the recursion lecture, and we can do it again now, which is like for any Linux program you run on Linux, it might be Unix with Mac, I'm not sure, I don't own a Mac. We can measure the time it takes to run that program, right? We simply add time to the front of that command and it will tell us how long it takes. Now we did that previously, and just to like, because I've still got this example up from the last lecture, right? Let me just look at like the factorial thing again. So it's like I can, I can compile factorial with factorial1.c, and then I can run factorial. And then if I put time in front of it, at the end of everything, it will print to standard out, I think. Let me just check. No, it prints it to standard error, I think, not standard out, how long it takes to run. So this one says 0.002 seconds. Now, generally speaking, anything that's getting into that one is basically ridiculously quick, right? It's like so fast that you wouldn't even measure that because that might even be quicker than that. It's a bit like a plane, right? Like, how when you're on a plane, it's like it's really hard to compare the time it takes between like, what's an example? Like I grew up around Byron Bay, and I've flown to Brisbane before, which is really close. And like a flight from Sydney to Brisbane or Sydney Gold Coast or Sydney Byron Bay are all pretty similar in distance. So like it's really hard to tell for really small things because you spend so much time taking off and so much time landing that you're like most of it's just in taking off and landing, right? You don't actually spend a lot of time flying, and fast programs are like that. So when times are really short like this, it's really hard to say much about them, but you can still time it. And there are three really important components of time here, which is real, user, and sys. Now, essentially, real time is the physical time it took, right? So what that is that's the computer looking at its watch, and it's saying, yep, okay, we're going to start now. And then when the program finishes, it goes beep, and then it says we're done. That's kind of the gist of what that is. It's the real time that elapsed. Now, in general, real is quite similar, right, or quite close to user and like the sum of user and sys. And what user and sys are is user's typically the time it takes your program to run, right? Your program spends time processing. So user is kind of often the closest thing to how long your program takes. And then sys are things that the operating system is doing. Sometimes that's opening a file or making a network request, or mallocing memory or something like this. So it's basically like, because your program runs on a computer and it'll run in its little bubble, but occasionally it needs to say like, hi computer, can you get me this file from the hard drive? And the computer says, sure, one sec, and it goes and gets the file and brings it back and gives it to your program. And that little bit there is what we call sys time, because it's what the system is doing. It's not what the user means like your program, is doing. So you'll see like they're essentially the relationship between those three numbers. And we can do that for any kind of program we want. And it's really helpful to actually look at the real time something takes. So we're actually going to try and analyze a simple program, and this might be the main thing we do today, which I think is good because it'll get you thinking about it for next week. And we're going to analyze a really simple program that just sums numbers. So here you can see that the program includes studio.h. It's a main function. We have a sum variable, and then what it does is it starts reading in integers from standard input, and it will keep looping while scanf gets a valid number. Basically, while scanf hasn't been told to stop, and it will sum them all up and it will print them out. And we can actually play around with these files. I can actually copy them into this folder here, I think. Oh, that's not good. One sec. Oh, they're really big files. Oh, I'm probably going to run over my disk quota. Ah! That's okay. Maybe we'll do this inside of a different account. So some of these files are super big for the lecture demonstration, so I might actually just inside there's some like system accounts that have more quota than like yours or my disk quota. Only one or two of them though, so I'll just show you that for great. So I'm going to go inside my sum folder, and you'll see here that there's a file called sum.c. I might close all of these previous ones here. Sum.c. Oh, that's a funky looking gedit. Gedit preferences are, everything's so weird. Let's make this really big. Beautiful. Okay, so we've got this really simple program here called sum. And I can compile. Why is it different every time? Why was it gray randomly? I'm so confused. Everything stresses me out. Okay, let's make it even bigger. Oh, I'm so confused. All right, whatever. I'm done. So now it's okay. So a simple program. Let's compile it. Right. G++ wall where -o sum.c -o difference. Very big difference. Okay, now I'm going to run it, and it's not going to prompt me for anything because it doesn't have a printf, but it is waiting for a scanf. It's stuck in this while loop here. So if I enter 1, 2, 3, 4, 5, right? It will keep going until I send it a signal. Oh, sorry. I teach C++ too, and that's the C++ compiler. Let me try again. I don't want to be confusing. Thank you. So I run sum, I enter 1, 2, 3, or 5, and what happens is this will keep going forever until I press Control D on the keyboard. And when I press Control D on the keyboard, it kind of sends a signal to say, this is all of the input that I have, and then the scanf returns -1, and then it leaves the while loop. So I press Control D, and then it says 15. Now that's good, it sums up all my numbers. It's exactly what I want it to do. What I've also got here though is a whole bunch of input files with different numbers in them. I've got this file here with 100,000 numbers in them, this one with 1 million, this one with 10 million, this one with 100 million, and this one with 1 billion numbers, which is a huge file. In fact, you can see these files. This one with 1 billion numbers is 2 something bytes, and I can just Google that. Bytes to gigabytes. Yeah, so this text file here is 200 megabytes, or, you know, something crazy like a 30-minute movie. So, I'm just drinking. So we want to run it. We want to compile it and run it. Now, if I have all these like 10,000 numbers and I want to sum them together, how can I pass those numbers into the program? Well, we did this before. You can do .sum, and then you can use the side arrow, and then you can give it a file like that, sum10,000.txt. And that will take all of those numbers and it will send it into the program as standard input, so that's as if you're typing them in on the keyboard, right? Like as if you're just like typing them all in. So I do this, and it does it really quick. Now let's try for 100,000 numbers. Really quick, million numbers. A little slower. Notice it's just got like a tiny bit of lag, just chilling a bit. 10 million, a lot slower. 100 million, I don't know if that's 100 million or a billion. I can't tell with those zeros, but that kind of looks like a billion. Vincent asked a really exciting question, which is, will the files all have a control D at the end? So they don't actually have a control D, but as part of just how computers and operating systems work, when it's reading in a file, when it gets to the end of the file, it basically sends a control D by default. So you don't actually have to press it. That's the simple summary of it. I don't think there's one bigger than that. Oh, there isn't. Okay. So you notice how they all took different amounts of time. Well, here's what I want to do together. I want to plot this quickly. So what files we got? We got 10,000. We got 100,000. We got 1 million. We got 10 million. We got 100 million, I think. And I think we had a billion. I think we did. So let's time these things. Let's do it. So let's go back to 10,000. Let's see how long this takes. Time. 0.03 seconds. So I'm going to do seconds, and we'll use the real time. Sometimes you should use this user time, but for simple programs like this, it's not like a massive deal. Input. So I'll call this for 10,000 inputs, it takes 0.03 seconds. Now we'll do 100,000. Takes 0.010 seconds. For a million, takes 0.078. We need to run it 3 times for scientific validity. There you go. Sure, we'll run the other ones a few times too. 0.10, that's close enough, and then we'll do 10,000. Okay, sweet. So we've done 10,000, 100,000, a million. Now let's do 10 million. 10 million takes 0.77. Whoop, some discrepancy. The computer's learning. Let's just call it 0.76. And then we'll do 100 million. While that's doing that, I might just format these rows so that they're all the same decimal place. 7.536. Oops. Turn numlock on or off? I don't know. 7.563. What was it? It was something. 36. 7.54. That'll do. And then we'll do the last one, which is 1 billion numbers. This is gonna. Oh, we don't have 1 billion. I think I'm crazy. Oh, I think my. Oh, no, sorry. Okay. So remember how I said that 100 million numbers was 200 megabytes? Well, 1 billion numbers, which is 10 times more, is 10 times 200 megabytes. So it was 2,000 megabytes, which is 2 gigabytes, which was too big. So I couldn't do that. I was like, I'm not going to put a 2 gigabyte file of single digit numbers on the CSE machine, because someone's going to find it and they're going to be like, Hayden, what is this? And I'm going to be like, I don't know. A lot of numbers, that's what it is. Yep, let's plot this. I'm not going to lie, I didn't plan to plot it, so I don't know how to use Excel. But let's try it. Chart. Beautiful. Okay, so this chart is terribly deceiving, which was not really what I hoped for. So maybe let's not look at the chart. So here's a couple things. Firstly, for really fast programs, you can't derive much from it. It's like what I said about line charts. Thank you. But even the line chart wasn't. Let me get to it. So for really fast programs, it's deceiving because of what I said about planes, right? Like it's really hard to tell how efficient a plane is flying through the air when it's flying from Sydney to Canberra, because it barely like spools up, it spools down, etc. So you can kind of see these first two cases are actually really hard to count, because this one says it's 3 times faster, and this one probably like could be even quicker than that, right? Like a computer could process that really quickly. But if we look at these 3 bigger ones here, 1 million, 10 million, and 100 million, which are all 10 times bigger than each other, what you notice here is that one is 0.07 seconds, one is 0.7 seconds, and one is 7 seconds. So we don't really need a chart. We can try and make one to tell that it's linear, right? Like it grows linearly. Where are the line charts? Line. One of these is a line chart. Oh, there. Thank you. So these line charts are kind of deceiving because of the scale of them. But this one's really hard. This one's really hard to plot because of the nature of the The nature of the program is such that you don't notice the time difference except for large numbers, which are hard to store. But yeah, so just to not complicate it too much, it's totally linearly proportional, which means that as if you tenfold the input, you tenfold the time. So for a billion numbers, it's going to take 70 seconds, and for 10 billion numbers, it's going to take 700 seconds, and for 100 billion numbers, it's going to take 7,000 seconds. So if you were to plot this with more data points, which again, we could sit around all day plotting this, but you're all smart enough to understand what's happening here, and you made a line graph that had lines at right angles, and you did like time taken in seconds, and then number of inputs, it would look like something linear. I'm going to use an actual line. It would look something like this, right? As you increase the number of inputs by 1, the time taken goes up by 1, right? It's totally proportional, as Autumnal said. So that's a way we could analyze this program. So if I said to you, can you use the time function to analyze this? You could do something like this. So we've kind of touched on these questions. How can we run and plot these results? How would you describe how long this program takes? Well, we kind of said that for every number it increases like that. So if we 10 times the input, we get 10 times the time. How much memory does this program use? That's an interesting question. Well, for that, we don't actually have a tool that we're going to talk about, but generally speaking, you can just look at it. So in this sense, this program uses, it looks like 8 bytes of memory, because we have to make these two variables here to run. In reality, it would use slightly more than that. But one of the key things about this function that I want to make clear is that while the time this function takes to run increases linearly with the number of inputs in a straight line, not a quadratic, not some curvy thing, in a straight line, the amount of memory we use is always the same. We always allocate 2 variables, whether we're trying to sum up one number or a trillion. And therefore, if we were to try and plot if we were to then try and plot, say, memory usage in, I don't know, bytes or something, what this would actually be in reality is it would be a totally flat line. Now this would be really close. Yep, this would be really close to the bottom. I'm just not drawing it there, because as we have more and more inputs, we don't actually use more memory. We're always using the same amount of memory. So what we would say for a program like this is that it uses a constant amount of memory regardless of the size of the input, but it uses a linearly increasing amount of time per the number of inputs you have, right? Something like that. So that's the gist of it. Now what we're going to be doing next week is honestly just going through more examples. We're going to look at a sorting program. This will take us a while. So Let's wrap it up, but I hope this gives you a taste of what we'll be talking about next week, which is all about analyzing and writing different programs. And it's a really, really critical and important part of the course. So, yeah, besides that, I'm going to stop the recording just because no one actually watching this later needs to hear about like what we're going to do next week, because we'll just go straight after.